All right. Yeah, I graded the test 5 at lunch, so you should have an updated score now in your scorebook. All right, so swing back to last time we talked about our fragmentation. Typo, let's fix that. All right, we have internal data and external fragmentation. 3 ways the memory is going to get fragmented. And most often, external fragmentation is going to lead to data fragmentation occurring, but that's not always necessarily going to be the case, right? Just like we did in our example, just go back and forth between allocating objects. That's also going to lead to our external fragmentation, our internal fragmentation without having external fragmentation actually pre-exist. So all 3 are more or less independent of each other, but they're all in related spaces. So sometimes one can cause the other type thing, the exception of internal data fragmentation, which is wholly contained within itself based on how we define our data types, how much space they're actually going to take. So unless I'm forgetting something, that should be everything that's for test 5. Test 5 is primarily going to be hashing. Sure, asked a question about last week's test. And number 4, it was a wheel. The key was wrong. The key would have, I fixed the key and I did the regrade, so it should show updated points. Okay, yeah, so test 5 will be hashing. Probably a third to half the test is going to be hash functions, hash tables, cryptographic hashing, all the stuff we talked about in the hashing area. Then there's gonna be a few garbage collection questions because we got 2 ways to collect, and then locality reference, mostly gonna be like short answer type things, and then fragmentation, short answer plus figure out where memory is going to get allocated when we do have a fragmented heap. Got the practice tests that should be visible. Let me know if the practice test is not visible. We'll go over that one next week. And then we'll take the test on the following week. And we'll go over the test, and then we've got the final coming up after that. Is that right? 4 weeks left. What we got here? Where are we? Yes, 4 weeks, including today. Yes, 3 more lectures after today. All right. So it's carrying on to the final section. So as a reminder, that final exam is cumulative, so it's going all the way back to the beginning. It's not just section 6 of the notes. What's the format question count and how many coding questions will there be for the final? So format is still largely similar to what you see on the other tests. It's probably a little bit over twice as big. I think it's like in the 50 to 60 questions. We'll have 2 hours and 10 minutes for the final. It's basically, I take half of each of the 5 tests, grab questions, like questions you saw there, and then bring that to the final, plus this last bit for memory compression encoding part. And yeah, how many code questions are there? Probably like 5 or 10. But with it being the final, the code questions tend to be more. I'll give you more of the code bits, and you just need to piece it together. Okay, let's see. All right, so memory compression, we're typically changing the way the data is represented such that we can get away with using fewer bits to represent the same or nearly the same information. Memory compression may be lossy or lossless. With lossy compression, there is some information that is lost in the compression process, and additional artifacts may also be introduced into the data. However, the algorithm produces resulting data should do so in a way that the data loss is good word for this. Not appreciable, but let's put insignificant. Insignificant. All right, let's get good old paint up here. Zoom in a little bit. Okay. Let's see. Let's just draw a circle. And probably just fill. All right. It was recently Easter. I guess this works out into making an Easter egg. Yeah, let's go a little bit further. Might as well. Over here. There we go. Now it looks more like an Easter egg. All right. So look at that. Last time I used paint was last time I talked about compression. So 24-bit map. Easter egg. This is going to be our least or completely uncompressed version of this image file that we're going to be playing with here. Go bring that folder up. And we can look at our Easter egg. Our Easter egg in all its glory is 0.5 megabyte in space. The way a bitmap encoding works is it's a bit by bit representation, basically just one massive array. So if we're, let's see. Well, it's going to look like Notepad++. Probably should have made it a little bit smaller, but yeah, that's pretty good. And those nulls are might be the ends of the rows. It's somewhere in here. We'll actually have egg data. There we go. Here's some of our egg data. But pretty much we've got a white pixel, 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 repeated over and over and over again. Here's a whole bunch of white pixels. And then we've got probably an end of row marker possibly here. I don't remember all the details of how bitmap's done, but here's a bunch of white pixels. And we can see it's doing a lot of highlighting. We've got a lot of rows in my file that are just white pixels. In the middle of our image, we have other stuff. But the encoding of this file, there's basically no compression. Each pixel in the image, whatever color it is, takes the same amount of memory as every other pixel in the image. All right, so 561 by 323 pixels gives us 531 kilobytes of file storage. Right? It's not a very good way to store files, but it has all the data that is going to be inside of our egg. Right, we can zoom in. Right, it's of course still a pixel-based image, so we do see that smooth edges are going to have a little bit of angularity to it, or, but it's as good as it's going to get. We can start doing some simple compression ourselves by reducing how much memory this is going to take by changing our color palette. Right now we're at 16.7 million possible color combinations per pixel because we got 8 bits for red, 8 bits for RGB green, and then 8 bits for blue. And then, just to the 24th power, 16.7 million. So you look at the graphics cards, they're all like, yeah, 16.7 million colors. Just how much you get with 24 bits of information for a 3-color positive light color scheme. So instead of a full 3 bytes per pixel, we're going to go down to 1 byte. 1 byte, right, to the 8th will give you 256 possible combinations. And we will cut the file size down by 2/3. Paint's telling us that, you know what? I can't represent 16.7 million colors when I only have 256 colors to choose from, so your image is going to lose some data. So depending on whether or not the colors I chose from the palette bar here are in that 256 color set, this image could get a little bit blown up. We'll see in a second. Yeah, it wasn't too bad. The pink got a little bit darker, right? But I compressed the file. It's now 1/3 of its original size, and I lost information in the process. This original shade of pink, right, which was probably not even, I can't even do it now. Right, open up as a back to original so we can see the difference, but that was a lossy compression. We lost data. What we lost was the particular shade of pink that my egg is. As you can see, saving 67% of the data at that loss of information, or the 67% of the space at that little bit loss of data is quite acceptable. Right? Just depending on how things go.
Do you expect like for that type of data to be lost like around 20% almost every single time, or just an average?
The data loss, it just depends on what we're compressing. When we'll
Okay.
look at a full color scheme as I had earlier, we'll quite see the degree of data loss as it goes. Right, and since my color palette, 1, 2, 3, I only have 4 colors in my color palette. We'll see how far we get. White and black, those are the ends of the color palette, one to the other, and then we actually have 2 colors in between. And depending where things land up, this image can start to fade away really quickly, but we'll at least keep the white and black in the end. Right, it's quite possible we get all the way down to monochrome. I'll have my white outside, my black border, and maybe these yellows will go ahead and stay black, but they might get completely washed out. We'll see as we go. All right, so I went back to my original. Get my highlighter on here. It's easier to
Professor,
find.
for the loss of data, is that dependent on the row and the column?
The
For the
data
pixel?
loss, what we're doing here is it's not going to depend on the row and the column. It's going to depend on the color of the pixel.
Okay.
It's depending on the colors of these pixels. What Paint is doing is it's looking at each pixel and then comparing the color of that pixel to the range of the color palette that it has. Right? It's like matching paint at the hardware store. You want your house or room or whatever to be a particular color. So you take a sample and you try to match the color to color palette, but you may not have an exact match. So you're just finding whatever is closest to that color to represent the final product. Okay, so at the bottom of Paint down here, we'll see we have back to 0.5 MB. So we're going to go again and save. Instead of 1 byte per pixel, we're going to go down to 1 nibble or 4 bits per pixel. And there's going to be data loss. It's just a matter of how much data loss it's going to be towards getting to our data, right? So down to 90 kilobytes, and it still looks like an Easter egg. The inside managed to go to gray instead of pink, right? So it definitely doesn't look like a very joyful or colorful Easter egg anymore at this point. It looks like one that's been sitting out in the field for a good long while, but we can at least still tell it is an Easter egg, whether or not we're zoomed in on it. And we've got our nice small image. Where we're here at, what, 1/8 the original file size? Somewhere there. No, 1/6 of our file size. That went from a third to a sixth. And we'll go back to our original. Then we'll go one more time. So we're going all the way to the extreme, as small as we're going to be able to make it using bitmap. All the way to monochromes. It's talking about 1 bit. 1 bit per pixel. And there's going to have some data loss. And yep, there we go. So it's an oval at this point, and it's 22.8 kilobytes. So a significant amount of compression. Right now we're at 1/24 of our original file size, but we've lost our egg color, we've lost our spots even, or we have to come back here and touch up the image and try to get our spots back in wherever they happen to have been. But we're limited to just 2 colors at this point. Almost makes it like a little sideways face now. All right. Right. It's not exactly a compression algorithm. What we're just doing here at this point is basically we're just customizing our color palette with standard color palettes. Going here. All right. So what we do here, let's get a screen grab for color palette there. All right, here with the color palette, we don't have all 60.7 million colors here, but we have one range of our colors. If we start doing the same thing with our color palette, we'll start to see how much data loss we'll really get. And I'll just keep jumping through. 256 colors, and we'll murder it as we go along. It's fine. Right? You can see here the image distortion jumps up really quick because it's trying to approximate as much as it can. And then large areas get converted into different colors that they weren't before. And we'll just go down to 16 color, replace it as we go. All right, so there's our range of colors at 1, 2, 3, this big old swath. Anyways, not exactly a typical compression method, but it's just a good demonstration of showing how the data loss can occur going from an uncompressed to a compressed style. Now, the other thing we can get is also artifacting, which we will see with other compressions. Go for that. Okay. All right, so here with the star, when we look at our color with our bitmap representation, right? Because there's angles, we're still talking about pixels, and each pixel is a little square. And if the pixels are small enough, we can't tell that they're squares. Depends on the resolution of the device you're talking about. but the edge is clean. When we start going to other formats, let's see, let's call this one star. Full uncompressed bitmap. If we save as JPEG, I'll use JPEG because it's one of the older ones. Join pictures element groups in case you really care. We will start compressing our data. Now with this one, as far as I can get, I'm not so sure if you can see. But inside the edge, there's a little coloration, kind of like a static, if you will. These are artifacts right inside the edge of the star. This isn't the same crisp color as it is over in this area. Over in this area, the color is pretty consistent all the way through. I don't know how much, because of course this presentation is being compressed on my side, sent to the server, broadcast back out to everyone in the meeting. So there's all kinds of data compression going on there. So you might be getting any additional artifacts beyond that I can't see on my screen, but on my screen I can see. In fact, might as well get the zoom going. Externally to paint. All right, so this is the artifacts I was talking about before, where data that was not originally there is introduced into the internal, the compressed version. But this one still has a really good size to it as compared to our monochrome did. And I only had 2 colors here, so it's not exactly the best test to show. We can, let's see. Let's go get our, that's our image of the day. That looks good enough. Oh, I want the doodle. All right, hold on a second. Let's go back to the doodle. Try that again. Okay, try that there. All right. It's not a large color palette here at the moment, but there's data. And before we get too far, let's go see what the image is already. Looks like it's a ping. It's a portable network graphics is probably the most common, at least on large websites of image format you'll see, because it has a pretty good compression rate, and compression to quality is very, very high here. So I went ahead and unpinged it by doing a screen grab. Windows is doing a screen grab, just grabbing all the pixels underneath the area of the image. All right, so I can already see some artifacts in here from it being a ping, so we can see that there are some colorations, which means this is not going to be a good. Let me see if we can find some bitmap images. Yeah, maybe that's no one you. All right, we'll make our own image. That way we haven't any artifacts to start off with. All right, just get some overlapping here so we can see how well the various file formats are going to affect things. Anyways. Do, 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 do. Some good old modern art. All right. Our different algorithms, we're going to get different results, which are going to be data dependent. Best art of the year, right? 1.9 megabytes. Because this particular image is 1000 by 653 pixels. Right, what's that? 600,000 pixels, 3 bytes per pixels gives us that 1.9 megabytes. Why do artifacts happen? The artifacts are created just by the algorithm, because the algorithm, we'll talk about different ways we can start compressing this data, is, I think the way JPEG works is it creates like triangles. So it tries to find a triangular area that it can make and say, okay, here's the coordinates of the triangle and here's the color of the triangle. That's commonly how graphics cards work, if I recall correctly, or how DirectX works. If we're still the way that works, I don't know anymore. But it's a lot easier to say, okay, here's a box of space that's goes from here's the origin, and it's X by Y size and color, B in our color palette, and then just say that's a big old chunk of space. That's all one thing. So the different compression algorithms are going to do that type of thing. It's going to look to see how can I re-represent this data. So it takes less space, and as it does that, it might introduce things that weren't there originally, because it's going to be a better space saver than if it doesn't introduce those artifacts. So that's just the way the data processing works. Okay. All right, so we'll see what happens as we go along, but see, here's the JPEG first. All right, the JPEG, let's go. Well, it depends. Does the image still look like what you wanted to do and then save you the space? Right, so if we look at, let me get another paint up. Paint. Where's it? There you are. Let's do a side by side. Right, so at that level of zoom, right, with the naked eye, pretty much can't tell that there's any difference between the images. Zoom in a couple times. Even at this zoom, still pretty hard to tell that from the original to what we have over here, there's much difference. The star color here looks a little bit darker on my screen on the left than it does on the right. Keep getting in closer. Here's where I start seeing the artifacting the inside of the edge of the line. I can see that there's an additional color here that does not exist in the original image. The original image, this is one exact color for this entire. And as we get in deeper, more easily it'll be able to see the information loss. Right, so the artifacting is happening here. As much as you can see this particular line, originally it was red, and over here, we got a brownish color to it, and on the edges, there's an extra color here just next to the line. So we go from straight white above and below, but next to the line, there's some coloration there. And this is where the artifacting becomes intentional. It's kind of doing a little bit of a shading effect. And that shading effect is going to make the line look smoother when we're further out, further away from the image. All right, so we get the same scale here. Doesn't seem that it did the greatest of job of the shading here, but the idea is to make that line where we know that because there are pixels going on there, make it look smoother than what the original did, because it's just doing it's a full, it's a line, it drops, it's a line, it drops, it's a line. Here we have the same thing, but they've colored underneath this line and above that line to make this transition look a little bit smoother. All right, so let's go ahead and go back. Back to the bitmap, clear our drawings, and then change formats. As JPEG, go to GIF. All right, so if we go, and again, side by side, comparing the two. The GIF, we're here at 40 kilobytes, so our GIF did not compress as well as the JPEG did for this particular data set. It's twice as big. All right, image pretty much looks the same. Zoom in, we can see it's got its own kind of artifacting. So there's kind of a little bit of a fuzz to it in the lines. I can see it over here as well. But it saved us space. Other options. I don't see TIFF used much. But depending on the data, things will work out, they won't work out. All right, 41 or 43.1 kilobytes. Don't see as much artifacting with this format. We're getting about the same compression. And we're getting about these pretty much the same compression as we were getting with going all the way down to our monochrome bitmap, which was very, very, very poor facsimile of the original data. And we also have this one. I don't think I've ever seen outside of Paint, and didn't work at all. So we'll move along. And then the winner is probably going to be Ping. We'll see. See what we got. Nope, JPEG going to be in the winner today. See how much artifacting we got on this one. Least amount of artifacting, but we didn't get the best compression rate. And this is why you won't always necessarily see the same image format on the web. Sometimes you'll see JPEG, sometimes you'll see pings, you might even see GIFs. GIFs have the ability, added ability to actually animate the image as well, I'm sure. You've all seen a meme or two that on one platform or the other, and those are most likely GIFs, because GIFs have the actually ability to store that animated data by saving multiple frames within itself. Yes, the format, I wouldn't call the format an algorithm. There would be an algorithm to produce data in that format. And then there's an algorithm to decode that data. Right, so you need an encoder to take it from the raw data format, and then the encoder algorithm will go ahead and put it into basically the compression algorithm. The encoder is basically a compression algorithm. And then you'll have the decoder that reverses the process. You may hear codec and decodec. We're talking about media, trying to watch a DVD player on your computer or something like that, and it's like, you don't have the right codec installed. And so the coder decoder to actually basically take it from the media format that is, and then present it on to the screen the way that it can be done in the system. Right, so I don't know how extreme like Google, Amazon, all those other massive websites are. They probably are extreme. when they probably media department, and when they produce the images, they probably actually feed it through an application that goes ahead and saves it in the various standard formats and see which one is the smallest. And the editor might go look at it and make sure that image quality meets their standards. And then that's the one that is used on the websites, because right, we had a pretty close to a 50% difference between all of the algorithms, ping, GIF, and TIFF versus JPEG. JPEG was down close to 20, right? So if you have millions of images on your website taking up a ton of data, the algorithms are stored so they are just in the applications, right? So Paint knows how to understand these image formats. So if there's some other, like if I try to go grab a VSG, a vector file, SVG, scalable vector graphics, right? And I try to open it up with Paint. I don't think Paint knows how to read an SVG file, which is an image file. So it's a vector-based image format, which means it just stores the lines. So we take these stars, say I got a line, it's got an origin, and the scale of the vector, and the angle of that vector, and then just a bunch of lines, which means the idea of the scalable vector graphics is you can zoom in. It's film. You can go all the way in and all the way out, because and zoom close, and things don't start getting fatter just because you're zooming in. At least I don't think they get fatter, but you can actually just get closer and closer and closer to that particular corner in the star, and it's still the same shape, no distortion, no other stuff. So the applications that can process the data are the ones that store how to do that. I mean, the operating system very much likely has something in there as well. Same thing, like if I were to edit in 3D, this as whatever for you. I was talking about scalable vector graphics. I assume we heard that part. All right. Yeah, so same thing here. Yeah, .svg, like this Paint project, whatever it actually saved on the machine, right? It's a file format. So there are a lot of file formats out there. Most of them are going to be binary in nature, right? So the PNG, the TIFF, the JPEG, all these are just binary files. And the file extension is usually a clue as to what the encoding of that file is, such that an application that recognizes that file extension might be able to open it up. But whatever that image was, all right, if I tried to open, well, like I did with Notepad, I want to open up the image. Notepad can open it up because it's a file in the file system, but it's not really information that we're really understanding per se. But the file format and information, right? So we've got some header information that's describing the bitmap. Somewhere in here, it's saying how many pixels wide it probably is, how many pixels tall it is. Possibly I'd be mentioning that it's a 24-bit color scheme. Or being able to understand a binary file is an application-specific capability. And so you might even done the same thing in some of your programming classes where you saved employee records or book records or something along those lines in a binary format. And pretty much the only application in the world that knows how to read your file and make full sense out of that file is your own application. Right? Like Word used to be that way a long time ago. See, I was doing like HTML or JavaScript. If we go look at our data here, right? HTML itself is an encoding, right? Hypertext markup language. I call it a language, a little bit of a stretch to call it a language. Like more of an encoding or format scheme. But right, the HTML, of course, that's being given to us. It's going to be gzipped on the server and then sent to us, and then the browser needs to unzip that resource and then give it back, and then translate the data, and then generate the anchors, the divs, and all other fun stuff, and represent it on the screen. Right, same thing's happening with whatever CSS and JavaScript they have up here. In fact, those also tend to go through an encoding. Let's see if I can find a JavaScript and go look at that. Let's see, script. That's a font. I don't want a font. Interesting. Let's see. Let's go to Wikipedia. See if we can find someone that's got a. Yeah, the style sheet probably works as well. There we go with style sheet. That's probably minified. Kind of, sort of, a little bit. Looks like they don't do a whole lot of minification. Just got at least a little white space. All right. In fact, if we go back over here, probably, where's my pretty print? Oh, it's been a little while since I've been doing a lot of web development, so I forget how to use all the tools, but right, the CSS, cascading style sheets. It's just another way to format data. It's just a simple text format, right? So a human can easily read whatever's going on here, depending on how well they name things. We saw we had Google. Some of the class names were like they look like there were five character names. So they're definitely running it through a tool that's doing a replacement, because you can see a space, right? So they have this ordered list, MW, that collapsible. 2, 4, 6, 8, 10, 12, 14, 16, a 16 character name, right? So this is a custom name that they're adding in their style sheet, which they're doing in multiple places. Right? These names are somewhat long. Actually, if we go back to Google, look at our source, I noticed I can see the class names here. Looks like they're even using like a 1, 2, 3, 4, 5, 6, like using a base 64 encoding style for the naming here, because this class information shows up on the page so often that it's worth it to them. It's running through code to shrink it down from what versus like what Wikipedia had. So like so the original style sheet that probably wrote, because humans need to be able to maintain this code, they probably had in there something along the lines of, this is the class that we're doing here. So I'm using this class and I'm using that class, I'm using that class, but right, this takes up quite a bit of space. And there's only so much compression we can do with the gzip, so it takes it a step further and just goes ahead and gives it a different name altogether. And I'm just speculating at this point. I don't work at Google, so I don't know exactly what they're actually doing with their source code. But either they're doing this just to somewhat obfuscate their style sheets a little bit, make it harder for people to steal their stuff, which is kind of ridiculous, because anything on the internet that comes to your browser it's yours to go ahead and rip out, because it has to all be in the browser for it to be able to be presented on the screen anyways. But I don't know how many times this class is being used in the code file, but about 6 or 7 times, but it's half the space, and then doing that across the board. Oh, here's some minified JavaScript. That's good enough. Let's do that over Notepad. And this is another thing. It's just minification is effectively a way of compression. Right, so you see very, very bad variable names. The original source code that was used to generate this JavaScript, it's very, very unlikely that they're using single character variable names for things, because that becomes incredibly difficult code to maintain. But as far as JavaScript's concerned, or programming in general, a single character variable name is the same thing as right, whatever D might stand for, digitize or something like that. And so they might have some digitizing that represents some digitization process that's going through. So if you're having D all over the place in the code and using D, saying digitize, 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 right? Just like we did with the bitmap compression, we just basically throw away all the extra stuff. And the basic way of doing it is we just keep the first character name. And it's just as good. All right, so it's run through an application. The application understands the JavaScript or the CSS, and it compresses it, and it's doing it in a way that's just basically just substitution, replacing variable names, eating white space, right? This line, this is all one line. There isn't even any carriage returns in it. It's all the white space that can be lost is lost. So you see, right? Normally you like to see if space, spaces after this, carriage returns, little line feeds, right? But all that white space doesn't mean anything to the system that's running the code. Right? White space is almost entirely style and readability for the human. The computer just needs white space between tokens or something, another special character that will suffice, right? Semicolon's a good token separator. So between our keywords and our identifier names, we just need something that separates it. And if it's not a separator, then we'll have to put some white space in there, but it does a lot of murdering of the white space, right? And it's compression. There's lots of ways to compress data. And the idea of doing it is saving transit speed. It takes twice as long to download 2 megabytes as it does 1 megabyte. So if it takes, and especially think way back to before broadband speeds or spotty cell reception speeds, we're getting kilobits per second. You got a web page that's 3 megabytes in total size, which is all the ads and all this other junk that's being sent to your machine. A lot of it does tend to get quite large. It's going to take a lot longer for the content to be presented to you because the browser can't present the content until it gets it. And if things are quite long and long named, much extra white space, it makes it easy to maintain the code, but it doesn't matter the browser, 100 white space characters in the browser is the same as 1 space character in the browser as far as representation on the screen is concerned. So getting rid of all that superfluous data and then throwing it through gzip afterwards and then sending it down on the wire so the browser can go ahead and decompress it, because usually the communication boundary is the slowest part of the system between the client and the server, is getting the data to the client. So a lot of effort tends to be done to represent the data in a way that is small and smaller, or the smallest that we can come up with without going too excessive on how much time we're spending to get it to that small state. Because if we don't want to spend 3 seconds to get something to really small just to save 0.0001 millisecond, because it's taking, because now we're adding latency on the other side. So it's depending on, it's a real-time system versus a, something like a web page where we create all the resources, they're compressed on the server, and then they're served up many times. Right? In those scenarios, the operation that's happening frequently is the request is being made and data is being sent to the client's browser. Right? The content's created, and the content might be even years old at this point that the person has gone to, or especially Wikipedia, right? We'll go to Wikipedia's site, right? I don't know, let's see, history. It's the last time. Oh, interesting. A lot of changes today. Perhaps we should go look at a random article instead of one that was highlighted by Google. Let's see. Okay, this seems more realistic. Right? February 10th, a few months ago. I have no idea how many times people have been looking at Stevie Wonder's album, but it's probably been a time or two since the last time the page was changed. And just like with all our algorithms, we'll look at what are our operations, which operations do we need to be able to support, which operations do we want to optimize because we know that that's the operation that's going to be happening the most often, right? And being served up the content from the server is the operation that happens the most for any web application. So getting all this data into a nice compressed format is what we want to do, and spend the time, which takes seconds. The editor does something, it goes up to Wikipedia server, it goes ahead and runs it through an algorithm, stores the data, and then whoever wants to come in and visit, look at the page, and go ahead and get presented that information. Okay, so with the lossless counterpart, all of the original data can be recovered and decoded. Right, so depending on what you're doing with the information, right, are you just zipping up a log directory to save some space and then shipping it somewhere, and then later you might need to unzip it, right? We need to be able to read the logs after we unzip the logs, right? We go, all right, if I want to go to Windows and I want to download or I want to zip something, right? Send it to 7-zip or send it to a compressed zip file, right? Whatever compression algorithms that Windows is using to create the zip file, or 7-zip is using to create zip files, or one of its other archive file types. It's going to be doing that through its compression algorithm or algorithms, and doing it in such a way that is lossless, because whatever the data was that we are compressing this way is something that I want to be able to get fully back to the original state, which, so long as your archive doesn't get corrupted, we'll be able to do that. I've seen a number of times when an archive gets corrupted, and when we're doing with compression tends to be as on the aggressive side. So if you have errors in the data, someone lost a couple of bits on the file, and then we'll get to the point where it's possible the entire file is unrecoverable. Okay, let's see. Okay. First compression algorithm that we're going to look at is called run length encoding. Okay, with run length encoding, data is broken down into sections of repeated symbol or character. Then the length of that sequence is counted. Then we encode that information as a length plus symbol. So let me show you what I'm talking about. If we have this unencoded data, we have a number of runs in the data. We have a bunch of A's, followed by a bunch of F's. And C pops along. A jumps back up in the data again. More F's again, and then lastly some E's. All right, so the lengths of our runs, however many that is, let's see. 4, 6, 8, 10, 12, 13. All right, so we have a length of 13 A's. Well, if we go back, depends on the nature of data. And we go back to our bitmap, we can see the runs are repeated quite significantly. Right, we get the same pixel being repeated over and over and over and over and over and over and over again. So it is very, very strongly data dependent, which is going to be the case for pretty much all the compression algorithms. Compression algorithms are going to try to take leverage of repetition. We see the same thing over and over again, and whether it's be a ping, a GIF, JPEG, or run length encoding, right? In order to get really any compression, we need to see the same data more than once, like compressing logs. I mean, you can often see log files have a very high compression rate because you often see the same data being repeated over and over in log files. You got a timestamp, you got a date. It's February, it's March, where we were May 2nd, 2022. We're going to see May 2nd, 2022 in that log file. You might have 20,000 lines of logs in that one log file, and that same date is probably in that log file 20,000 times. So what you can do is, you're taking calculus, kind of like U substitution, where you can use U to substitute a larger expression. It's the same, a lot of compression techniques, so you do the same idea. You just replace that large thing with a U, and then everywhere that expression was is just that U, so you can keep things simpler. So here we do the same thing. We see that 90% of this file is that same pixel. So we can go ahead and say that one pixel is pixel 1. In fact, one of the ways we could treat this file and see that we only have, I had what, 4 colors in the file. So really there was only 4 different pixels to keep track of. So I really could have gone down with a custom color palette and used 2 pixels 2 bits per pixel for the entire thing, and you've gone to a custom bitmap there, we're just using 2 pixels. And even then, that same set of 2 pixels is going to be repeated over and over and over again. So then we gone ahead and applied the run length compression on top of that custom symbol table to get even greater compression. So oftentimes a compression zip software will run through multiple compressions on the data, because just by compressing the data, we can create a new set of patterns in that encoded data stream that can then further be compressed again after that. All right, let's see how long these other things are. We got 2, 4, 6, 8, 10. And looks like I don't have a monofont here, so that's 2, 4, 6, 8, 9. Wait, 2, 3, 3, 3, 9. So we got 6 A's, 5 F's, and then 6 A's. Yeah. Yeah, memory compression is definitely, just like when we locality reference, all the things we're talking about locality reference, those are one of the things that are ever present in computer systems, and compression is another thing, because I've heard it several times, I forget what it is, how much data is being generated on a daily basis. It's massive, and are people taking 5 megapixel images and then saving those off up to the cloud for, however many selfies that they're taking every day. That's going to take up space really quickly, which is why you have quotas on your cloud storage, and people are like, you want full image, or you want compressed image? Because when you get the compressed image, there's going to be compression and the possibility of data loss when you go with that compressed version. Yeah, that's one of the things I've thought about, trying to think, right, if you have a 100 by 100 pixel image, how many possible different combinations can there be, and how much data storage would actually require to save every possible combination? And it's going to get to the point where your selfie has already been taken before, because it just matches one of the patterns that has pre-existed. I haven't done the math. I'm sure it's way astronomical in size, especially if you have yeah. Anyways, though, if you anyways, I was right there. So it's quite astronomical. So we have 6 links, or 6 runs. 6 runs in total. Right, so our encoding output the length followed by the character. So what we'll have is 13 A's, 10 F's, 9 C's, where are we there? 6 A's, 5 F's, and 6 E's. And so here is our encoded data. So next up, how successful were we? So we can talk about compression rate. In fact, might as well move compression rate over here to the general section, because it's not specific to run length encoding. So compression rate is going to be length, and please press length of the input, and it's the length of the output, which is then divided by the length of the input. And so let's go back over here and plug that in. So our original, we're going to assume, is ASCII. So right for the above, assuming we're doing 8-bit ASCII and 8-bit lengths, we have in the original 23, 32, 38, 49 characters. Okay, 49 bytes. The encoded data has 6 runs. Each run is a 1-byte number and a 1-byte character. That's 2 bytes per run for a total of 12 bytes of encoded data. So we have here is 49 less 12 divided by 49. And let's bother the calculator for that. Minus 12 divided by 49, 75.5%. Compression rate on that specific set of data. All right, another example. Okay, so let's break this down into a table. We have our run and its length. And so we get 3 A's, length 3, pair of B's. Well, we got there 5 C's, 4 A's, 1 F, 4 A's. And here's where things get a little bit dicey. A single F, a single A, and that happens a few times. All right, so encoded 3A, 2B, 5C, 4A, 1F. That's funny looking 4 over there. Let's fix that. Four A's. 4 A's, 1 F, 1A, 1 F, 1A, 1 F, 1A. All right, so our compression rate. Original is whatever total number of links we have here. We have 3, 10, 15, 20, 1, 2, 3, 4, 5. 25 minus, same thing here. Depends how many runs we have. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 runs. So we have 24 bytes compressed divided by 25, which can give us a 4% compression rate. Right, not very exciting. This FA at the end there, which was nice in a repeated pattern with our basic simple approach, didn't fare terribly well. Fortunately, we had a few other runs here that were giving us some compression. So using the encoding that we have here where the length, yeah, we could probably, I'm sure, I don't know specifically the names of the algorithms that would detect, other than like we had before, that use substitution where we see FA is being repeated over and over again. So what we do is say that that's G. Now we have GGG, triple G. And so that's 3G. And then elsewhere, we see G, we represent that back out as FA. So it definitely, it's like I was talking before, where we saw the same date over and over again. We'll look for the same pattern because the date's not happening right after each other. It's quite interspersed in the data. But we want to look at segments and see if we can find segments of data that are repeated. Then we can substitute alternate values and then see if we can get runs on that. And so here we have the length, the same size as the characters or symbols. Then we need the average run length to be greater than 2. Otherwise, we'll run into a negative compression rate, which means we're not saving any space, right? So for example, go ahead and sample 3, negative compression. Right, so go ahead and get our unencoded data. Is Bob is the greatest. All right, that's the data that we want to encode. Encoded. We have 1B, 1O, 1B. All right, 1I, 1S, 1T, 1H, et cetera, et cetera, et cetera. Da, da, da. We have basically no runs. Go ahead and look at our compression rate. I had 0 runs in here that were greater than 1. So it's going to be twice as big. So we got 2, 4, 5, 6, 8, 10, 12, 14, 16. Compression rate equals 16 minus 32 divided by 16, which equals minus 100%. And of course, 100% compression would be impossible, but negative on the negative bounds, there's theoretically no limit. Right, kind of like you have with the BOGO sort, you can just go crazy in a not effective way of doing things, right? And as I said a few times before, it all depends on the data, right? If my image that I was trying to save off was a color palette, here's all of the different color palettes that we can have that we're going to support in this encoding scheme. Then getting runs are going to be unlikely, but getting patterns in those runs, where we see that the pixels are shrinking by a few every single time, then we might be able to compress in a different way. Oh, what other types of data does this encoding work with well? Let me think. See if I can leave another example besides a bitmap. No, it's gonna have to be something that's binary data. Text data tends not to be very repetitive in runs, so it's gonna be some binary formats. Probably going back to what I was talking about, like you're saving employees and things like that, where the records often have blank space in it. Right, so like if we had Bob, right, where we had Bob, archare 25 equals Bob, right? Most of Bob is null. So you're going to see 21 nulls in that segment of data. So you have a nice large run there. So we probably see some runs with some binary stored data that way for actual user type data. But Yeah, and then I can't think of too many other places that I've seen. Okay, so all right, so extra, how is it? Okay, yeah, yeah, we've been talking about this too long. Okay, extra compression. Let's dive in to what we're actually storing. So let's go look at this encoded data. And let's just do table data. And the corresponding binary, right? So we're doing 8 bits. Getting things backwards here. 8 bits. Let's see, 65. How many was 128? What was that? 010. Something along those lines. 3 A's, 2 B's. Yeah, let me not trust myself. Let's go make sure I have the correct. And that's not what I don't want hex. I want decimal. Clear. 65, 0 and 0. Okay. Nope. I do have my one in the wrong place. Let's go get that back. Clearly my brain doesn't want to work tonight. Oh no, it's in the right place. Okay, 0, 1, 0. All right. Okay, so our B. Letters aren't particularly exciting, but the numbers are more relevant. Now I've got my longest run here. 0, 1, 0, 1. Right, 1 plus 0 plus 4 is 5. And on and on and on. 5 was our longest run in this encoded data. 5 is our biggest number, so that's the one we really care about. But this is what we're actually storing on disk, right? Disk is always, or disk, the network socket, whatever it is, it's always binaries. It's 0 and 1. Computers are 0s and 1s. The fact that we see a 3, an A, a happy face, or anything beyond that is just an abstraction of the underlying binary. Yep. All right. So setting the characters aside for the moment, because the way that we're going to deal with that is different. Delete the row, and we just look at our numbers. So just looking at the counts. Right, you'll notice that we have the same 5 bits at the beginning of every single one of these counts. If something is always false, then we don't really need to bother wasting space saving that. All right, so since the first 5 bits of every count, every count in this encoded data set is not being used, we shouldn't be using 8 bits to represent a count. And instead, just go with 3 bits. So now what we do instead of encoding our counts as 8 bits, we encode it as 3 bits. And so now, instead of a run being 16 bits, it's now 3 bits for the count plus 8 bits for the symbol for a total of 11 bits. So our updated compression rate for that same data as we had before. Who was this one? Who did I use? I used that one. We had 4% before. Updated compression rates now. So our length original is still 25. So we had 12 runs. Right, so we'll do 25 times 8. So we can get into bits. Minus 12 runs times 11. Right, divided by that same 200. Grab my calculator again. Right, 25 times 8. That's funny looking, 25 times 8. 25 times 8, right? Those are 200 bits of original data. 12 times 11, 132 bits. Right, so our 200 minus 32 bits, 68 divided by 200. Now we get 34% compression. Right, a significant improvement, even though our runs were in pretty bad shape, right? We had these 1Fs, 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 1Fs. We got rid of a bunch of space for our lengths to go ahead and optimize on that. Right, so considerations. For addressing the run length average. Right, you're having pretty much a bit of a bell curve, right? We're not necessarily bound by the longest run, but rather want to look at the average run length for the encoding. All right, so for example, let's say we have, and we'll say do 4 runs. We get, I'll just go ahead and straight put it as a table, not bother with the data. Character and count. So let's say we have A, big A, little a, whatever, and then say we have 45 of them. Then there's B, counts 3 times, C is 2 times, D 1, and then E pops up, whatever, 5, and then A is again here 11 more times. All right, so count length options. All right, bits range. All right, 1 bit, not going to give us very much. We have 2 possible values. So depending on our average length, we'll see what we got. 4, 8, so on and so forth. 4 bits to be 16. Right? Remember, we can get the full range because we're not going to have a length of characters that's 0 long. That's the absence of data. So we can get the full range of bits used because 0 isn't useful, so we can get 2. So this we had a 45 here, so let's keep going. 5 gives us 32, and 6 gets us 64. So if we use the max, we have to do 6 bits. All right, so using the max, run length, we have 6 bits per run, and 6 bits run plus per run for count, plus 8 bits per symbol, aka character. All right, so that gives us yielding an encoded length 14 bits times 6 runs equals 84 bits. Now, let's see. Let's consider our other bits. Let's consider using 5 bits, which allows runs up to 32. So encoding will just see the same symbol occur more than once in a row if the run is greater than 32. All right, so before we had, right, 45A, followed by 3B, 2C. And I'm just putting white space in here just to keep things easier to read. 1D, 5E, and 11A. With 6 bits. With 5 bits, what we can go ahead and do is just say there's 32 A's, followed by 13 A's, and then the rest is the same. And so we end up with one more run. Now we're looking at 13 bits per run times 7 runs gives us 81 bits. And so we managed to squeeze 3 bits out of that with 4 bits. Same thing, 4 bits, we're down to 16. So we have 16 A's. 16 A's again, gives us 32. Down to 13 A's. And then all the rest of this is the same. So we're going to have 12 bits. Now we're up to what, 8 runs? 2, 4, 6, 8. And we're over here, 96 bits. All right, so going the wrong way. At this point in time, but using something that's closer to the average, whatever the average, I can actually calculate what the average is. What is it? 50, 61, 66. The average is 11. So let's go down. Yeah, those 4 bits, right? Our average is 11. So 5 ended up being the winner. So close to the average. We were getting savings. So now what's driving our excess is now the data section, where we have let me rephrase data. Instead of saying data, the symbol section. So we delete the row, and let's get C in here. So we have something else to look at. Yeah. Okay. Let's go to our max letter. What was our max letter? E. Was it E? Yeah, E. So E, and might as well go to D. Since that's just one more row. And 1-0. All right, so just like I had before, now it's not all off bits, but it is the same sequence of data. Since we only have a small set of characters, this repeated pattern, and when we see patterns and repetition, it's where we want to go ahead and try to shrink things down here. Right, so building a custom symbol table is where we're going to next. But it's just that's the size, the fact that we're wasting so much space in the symbols, now that's driving us to the other side. So it's where we need to start compressing there. And by doing that, we can swing back to looking at our count links again and see if we can get us back down to this 4 bits actually being our optimal when our symbols are a little bit better compressed. Okay, let's see. Any questions about the run length encoding before we start talking about symbol tables? All right. Yes, this section 6 is only on the final. There's only we just have it's gonna be pretty much tonight and next time. It's only 2 days of lectures for this last bit. So we have right, we've got the test in 2 weeks. The 16th is going to be the test and review for the final. Yeah, there's a practice test for the final as well, which just covers the section 6 stuff. And then, yeah, you should use the other practice tests for the comprehensive part of the final. Yes, there's similar questions to the other tests. Yeah, so you can study, go do the practice tests again, study your old tests. That make sure you remember how to do all that stuff, and then go deeper into the notes. And then in the reading, that's my recommendation for the study, your study algorithm. Yeah, so tonight and next time, doing our compression and compression tonight. And then next week, we'll do our error detection and correction. And then this Monday, we'll have the test. We'll review for the final. Then we'll go over test 5. And then the night of the final is just the final. And that's where we are. Okay. All right, so the symbol table is a mapping from the binary representation to something more human, meaningful. there are several common symbol tables. ASCII and Unicode being the most common. All right, so let's get a link for ASCII. Not that you necessarily need to read up on ASCII or Unicode. They are standard symbol tables. So with ASCII, ASCII's 8 bits. All right, so here's the bits 7, 6, 5. So these are the upper bits. 0, 0, 0, 0, 0, 0, 0 is null, right? This is bit 7. So this is showing the 100% showing bits for like A. A is, there's a leading 0 up here that's not showing the chart because that's on a quote unquote extended ASCII. So we have 0, 1, 0, 0, and then 0, 0, 0, 1 is A. All right, you'll notice over here, little a, it's still in the same row, so it's the same 4 bits over here for bits 4, 3, 2, and 1. Only difference between big A and little a is this 1 bit over here. So that 2 upper, 2 lower are very, very easy conversions. They really only actually have to flip a single bit. Right? One has to believe that they did that by design. Right? And there aren't 32 letters, so they have 6 non-alphas in between. Right? Got square brackets, backslash, square bracket, caret, underscore, back hyphen, whatever, before we get to the other letters. Right? And the numbers, of course, also here. Just slapped in there, right? So all data is stored binary. This image, text, everything in the computer is stored in a binary format. If you see letters, right? If you see letters on the screen, it's because the binary was transformed to a symbol using a symbol table, right? Character table, ASCII or Unicode or UTF, one of the other ones. Or if you see something that, an image, same thing, binary was stored either as a pixel in a bitmap format, ping, TIFF, whatever, so they could then be represented again in something that's visual in a way that a human wants to perceive the data. ASCII and Unicode have the same first 256 values. So you can go ahead and take an ASCII file and convert it to Unicode, and there are no problems there. Pretty much all the standard symbol tables you can do that. It's just going to be twice as large. So if you have a 250 character, ASCII file is 250 bytes. Saving it as Unicode would cause it to jump up to 500 bytes. But we get to support multi-language with Unicode. Right, simplified Chinese relics, relic, I don't know how to spell that. You'll have to help me. All right, Greek, etc. Large number of, right, with 16 bits, you get quite a much larger range of possible values that you can store, right? 65,000. It's interesting how we're getting 144,000 when there's 65,000 possibilities. It's a lot more than 2 to our 8th power of 256 possible characters. There must be some header data. I'm not sure how they do that. Subtables or something along those lines. We know what is what. Because it's not going to be common that you can have Greek, Cyrillic, Chinese, Latin, Arabic, and all sorts of different scripts in the same file, so you can go ahead and do some mapping. Anyways, along those lines. Okay, so standard symbol tables is our standard encoding, but what we can go ahead and do is to further that is use custom symbol tables. Symbol tables can be used by looking at what symbols are actually being used in the data set, and then encode for just those. Right, so if the data is only using 25 different symbols, then using ASCII is going to be wasteful. For storage, right, what was it? We got 2, 4, 8, 16, 32, so 5 bits. Only need 5 bits to represent 25 possibilities. It's just a matter of storing the custom symbol table. All right, so let's say table data ASCII and custom. So say we have our A in our custom symbol table. We're only going to use 5 bits. We just say A is the first character in our data set. And say we're using E, right? Whatever the ASCII is, we don't care. E is 1. We're using G. G is 2. All right, next letter, whatever happens to be in our data set. Moving along, and I guess I'm doing this in binary, so I should stop doing decimal. 1, 1, et cetera, et cetera. We're using the number 2. 9's being used, whatever the symbols are. Commas in there. Doesn't much matter. It's just that's what's in our data set. And whatever data happens to be used, we just go ahead and collect it together, iterate through it. 0s represents A's, 1 represents E, 2 represents G, et cetera, et cetera, et cetera. And we just need to go ahead and pose the symbol table. Then store that custom table either in the header or elsewhere. And the data needs to indicate that in the data header as to what encoding the file is using. Just like we have to do with ASCII versus Unicode versus UTF. Right, so if I go ahead and get Notepad back up here, some data. You can see it's being stored UTF-8 and bottom right here in Notepad. We can change the encoding if we want to one of the various options, right? And see, which I think is the American stands for ASCII type thing. let's see, the ANSI text downloads. ANSI text already exists. Ha, that's funny. Apparently I'm consistent with my naming conventions. Let's do an ANSI and we'll do the ATF8. 4, 8, whatever. Typos aside. Let's see if we can actually get. And it only wants to show the contents. So we can see that just by changing encoding, when merged, had no problems dealing with it. Looks like it's showing us Windows 1252 here. Let's see. Online hex editor. I should probably download. Let's see if we can get it. 211. Yes, we can. I'm trying to get to see if I can show the header part instead of just the body, but I don't spend enough time in binary files to remember how to do that. But the applications need to know that are going to consume the files how to decode it, right? So if we go in and save as Unicode, is that usually an option of it? It's got to be. Let's go to a 16-bit format. No. Right. Bring that up as well. Right, so there's 16-bit format. And we'll see we get a little bit different information. We might be actually showing the header here now because now we have an FE in there at the beginning before we get 53. And then 6F, then we got zeros padding in between. So maybe the lack of header data is just treating it as defaulting to ANSI or UTF-8. I've always heard ASCII being pronounced as ASCII. So an AS and then key. But you know, it's an acronym, so it's ASCII, a sky. It's all about understanding. And I've always, I'm sure I was probably said it's ASCII by the first teacher that mentioned ASCII, so it's ASCII to me. What it really is, that's a good question. Let's see if they bother saying ASCII, right? So that they got SK, they got a hard K. Probably doesn't. Yeah, there we go. ASCII. Anyways. Right, so that information, which I finally get to show up, looks like I get to show up here. A little bit of header data, FF, bunch of ones turned on, 1 bit turned off there. So it knows that it needs to read 2 bytes at a time to get to some data. And it's just doing dots. Right, so look at it. Anyways, don't want to spend too much time over there. Right, so we need to submit the table and we get compression, right? So now the fact that we're using 5 bits, using 5 bits, we save, right, 37.5% in space that way on the payload. But we do need to account for the space of the header. And a simple way of doing it, while we're still in the ASCII part, We have 25, so we have 25 bytes of header presenting the table. So we'll need enough payload to offset that in order for the custom table to take advantage. All right, and again, this is just a simplistic way of optimizing. So just like we did with run length encoding, seeing that we had repeated data over and over again with our 8-bit numbers, knock off those 3 bits. We did the same thing here by replacing the table, effectively knocking off 3 bits that we know we didn't need, and we can get compression there. So if we were to fold back this custom symbol table and try to go back to our run length encoding and see where we are optimized on our how many bits we wanted for our runs. But this is just our foundation. All right, so next up, we actually start to get algorithmically relevant here. Huffman code. Huffman code is an algorithm to build a custom symbol table. Instead of just doing as we did in the previous notes, what we want to do is look further into the data beyond just what symbols we're using and look at their frequencies of use. Symbols that occur more often will want to have a shorter code word. Symbols that are less frequent will have longer code words. And Huffman will be making or be observing prefix clause, which means we will not have to use any punctuation in the encoded data. Encoded data. So by punctuation, let me show you what I'm talking about. Probably heard of Morse code before. All right, here is the code. This is a ternary code. It makes use of 3 things to encode, right, the alphabet and numbers or digits. We have dot, that's represented by here. We have dash, and we have pause. It's the way that Morse code. You ever watched an old movie here? Right, all that fun stuff. There are brief pauses between each letter, indicating that we've hit the end of the letter, because Morse code does not observe the prefix clause. But it does do a variable length encoding, right? So E and who's the other one? T. So E and T are our shortest 2 code words. Right, so we have the symbol E and we have the code word dot, and we have the symbol T and we have the code word dash. So if I say dot, pause, dot, pause, that's E. If I say, right, dash, pause, dot, pause, we got TEE. But we have to have that pause. If we just have dot in rapid succession, without punctuation, we wouldn't be able to differentiate if that is 3 E's or is that a single S. So 3 dots in the encoded stream is differentiated S versus E versus an I and E or an E and I by that punctuation. So our algorithm here. We'll go ahead and collect all the symbols being used. Determine the frequency of those symbols. And steps 1 and 2 would be done at the same time. You just iterate through the data. Every time you see a symbol, drop it in a hash table if it's already there, increment the count. Now we're really getting to the Huffman part. Sort symbols from low to high frequency. The forest from those symbols where we have a tree for each symbol. Can't type symbol in it apparently. And then repeatedly collapse the forest down to a single tree by combining the 2 trees, the lowest total frequencies together into a larger tree, combining their frequencies. After the tree is built, the code words are created by assigning 0 to left branches and 1 to right branches. Then then traversing down to each leaf, building out code words. Okay, so let's symbol frequency. We'll have to build the code word. Then code word size, then total footprint. All right, so we'll just use some arbitrary data. Say A exists 42 times, everything else to be determined. B is 27 times, C is 16 times, D 11, E is 33, and we'll go all the way to F, which we'll say is 5. Grab a screenshot of that. Zoom's kind of annoying sometimes with its overlays. All right. So let's go ahead and we'll build our forest. F has a frequency of 5. So that's our smallest tree. Then we've got D at 11. What do we have next? There's C for 16. B for 27. E at 33. And A at 42. All right, so we've built our forest. Next, we'll combine the smallest two trees, those being F and D. Smaller tree will go on the left. We'll create a new node to join the two trees together, creating an FD node, which has a frequency of 16. All right, so these two nodes will form together. It's the FD node, and that gives us a 16. And I don't like the way that white spacing is going on there. Smooth that up a little bit. Okay. Newly created tree now needs to be inserted back into the forest, which is being maintained in order. Right, so we see that we already have a 16 in the tree, so we have to pay attention to what the underlying structure is being used to store this data. So how are we storing the data? Is it just a sorted list that we keep pulling from, such as an array or a linked list? Or is it a heap? Right, the underlying data structure is going to drive how we insert the data. Now, using an array would force us to do a bunch of shifting around. Okay, let's see. All right, so we're going to go ahead. Yeah, it's quite timely, right? Insert this tree in front of the matching value. Otherwise, we'd have to shift the pointers around. And what's the fun in doing all that extra work? All right, repeating until the forest
down to a single tree. We'll take the B and combine that with C, observing the order they are in the list. All right, so these two are pulled out. New root FDC is created. Now have a combined frequency of 32. And we'll reinsert this into the forest. In sorted order. Rinse and repeat. First two out. Then together for combined frequency 59. My math is working tonight. And insert it back into the forest. That's appropriate to where it goes. And A, those two are pulled out. Yay, from I got there, 75. Insert back into the forest. And then one more time, and we have our final tree. And we can move on to the next step. Now that we have our single tree, enable the branches. That's 0 and 1. Zero and 1. All right. That's some zeros. On the left side. And we'll have ones on the right sides. Use that to build back to the beginning. What there's the table, so I just go ahead and grab the whole table here. Bring it down with our update. Right, so to get to B, 0, 0 gets us to B. So the B is 0, 0. To get to F, we have a 0, 1, 0, 0. 0, 1, 0, 0. Next path, 0, 1, 0, 1 for D. 0, 1, 1 for C. We have 1, 0 for E. And 1, 1 for A. Right, so since our characters or our symbols are only at leaf levels, at leaves, right? So got a leaf, pair of leaves, pair of leaves, pair of leaves, right? The internal nodes do not have our symbols there. They're just roots, which I've labeled so we can see what the subtrees have, but these nodes don't really even need any labeling for the most part beyond just the frequencies, so we can see how to join them together. Because none of the internal nodes are labeled, that's what enabling the prefix. So when we go ahead and output the data, we don't have to put any punctuation. That's the code word size in bits. Total footprint is going to be how many times we see by how many big that code word is. We have 3, we've got 7 times 4, 3 times 2, and 5 times 4. That's the total footprint. We've got 84 bits to encode all of our A's, 54 bits to encode all of our B's, 48 bits to encode all the C's, and so on and so forth. Find these two numbers. So we'll get to the encoding in a second. So our original size, we had, I think I forgot to do some math over here. Let's fix that. 120, 144, no, 134. That's assuming ASCII. 34 symbols. 34 bytes. Pressed size. We have 84 plus 84 plus 48 plus 44 plus 6 plus 20 bits. Calculator out. Make sure I don't goof up my math too much. So first off, original is 172, 1072 bits total, and then our compressed we have 316. And from that, you can all calculate the compression rate. So, the encoding process. Read from the unencoded data and do a lookup in the custom table and output corresponding bits. So if our data is whatever, C, D, A, let's say that's the segment of data that we want to go ahead and do. Unencoded. Encoded. Right, C is 0 and 1, and I'll just put spaces so it's easier to see it all. C 1, E 0. So I'm looking at the wrong. T was not 1 1. T was 0 0 1. These are the frequency. So that was E and 1 F 1, 0, and C0. Right. The actual would not have any white space in it. And so there's our actual encoded data. Decoding. Create the tree from the symbol table. Starting at the root. Read from the encoded data stream. If you read a 0, traverse left. If you read a 1, traverse right. You reach a leaf, put its symbol, and then return back to the root and repeat the process until the string is empty. Okay, so here's the encoded data. Go ahead and decode that data with the tree. Let me get the tree back for you. Click onto the screen as size that you can see. Okay. Let's go ahead and try to decode that. And the encoded data, assuming I encoded it properly in my head, it all will get the same result. If you have it decoded, go ahead and toss that into the chat window. And then we'll decode it together. Don't worry if you're wrong, it won't count against you. Hopefully everyone can hear me still. Hopefully you haven't put too many people to sleep. Anyone? No one cares to venture? Let's go ahead and do this together. All right, so we're going to go ahead and read 0. So we go left. Read 1, go right. Read 0, go left. Read 0, we get an F. So we're going to go ahead and output F. Go ahead and reset back to the root. And so we've gone ahead and consumed that part of the data. It's turned into an F. Next up, we have a 1. Go right. Go right. We have a 0. Go left. And we output an E. And we'll reset back to the root, and we've consumed that bit of the stream. We have a 1 and a 0 again, and we output an E. Consumed that bit of the stream. We have a 0, a 1, a 0, a 1, and we output a D. All right, so the seed was the word that was encoded. That's what we get from decoding it. All right, let me do another one. Yeah, lovely eraser. Doesn't want to erase. Whatever. Okay. In the keyboard, copy paste does not actually work terribly well. It was Visual Studio earlier today, but I don't know. Okay, apparently I'm just crashing Chrome right now. At least our third technical challenge of the evening. That's always fun. Well, while that's trying to think about things, let me go ahead and encode something. Oh, let's see, there are words. Probably not. Let's just do something random. Back to me when I'm trying to type. Typing through. We'll find out in a second. Okay. All right, here's our encoded word. Here's our tree. Let's see if we can't decode this one where we do it together. We'll start the root. Just keep traversing base zeros and ones left and right. I've got a CBDC as an answer. Could be the answer. I was typing and then Chrome jumped up on me and then I went back to typing, so I'm not even sure what the answer is just yet. You want to have another answer they want to add to the fold? All right. Go ahead and start decoding. So we have a 0, followed by a 1, followed by a 1. All right, so that gives us C. So we're so far so good. Consume the first 3 bits. Next we have a 0, and a 0, which is a B. Next up we have a 0, 1, 0, 1, 0, 1, which is a D. And then, yeah, I think I managed to come to my next topic. So let's see. C was 0, 1, 0, 1. Wait, C was 0. Break it down. Here, looks like I managed some data corruption. We got our C. We had 0, 0 for our B. We had 0, 1, 0, 1 for a D. All right. And then, yeah, 0, 1, 1 for our C. Okay, good. I didn't manage to lose any data. I thought I was doing E's and A's at the end there, but I don't remember anymore, actually. BBDC. All right, so it looks like we're all in agreement. I actually thought I had done an A at the end there, so it's quite possible I lost keystrokes when Chrome woke back up on me and changed my message. So that is what we decoded, and that's what we see in the encoding. It's actually interesting accident because I was actually trying to do an A at the end there. I managed to lose some bits And losing bits is very, very detrimental. Messages. Injection or deletion of a bit can completely change the message. And if I inject a 1 at the beginning of my encoded message, the entire thing changes. And so let's see what we even get. Do the same thing, and let's say a 1 got injected at the beginning. Right? 1, 0 is an E. 1, 1 is an A. 0, 0 is a B. We have a 0, 1, 0, 1. 0, 1, 0, 1 is a T. 0, 0, 1, and then a C at the end there. So we still have EABDC, right? So the way my correction happened to be, it actually kept the latter part of the message intact, but the first 2 letters are not actually accurate. All right. That's our Huffman code. Let's back over to our programming assignment. That's in a couple of weeks. All right, our hash table. Let's talk about how we could structure this. So first off, core of this program is an interpreter. And so we need to be able to read data from file and then output that. Let's see. Let's use Studio. Some files here. Okay. And so I'm not going to be giving you the code per se. That's why we're in some C# just to show you the idea of things. And let's open up. Create folder, create file. And org.code. Right, file extensions are just a clue to the operating system to basically what are we going to associate with that. So if I create an application that's a board code interpreter, we create a file extension handler and assign it with our program. Otherwise, it's just a clue to the operating system as to what it is. I'm just going to go ahead and hard code a few things here at the moment. Arbitrary. And being a little weak at the moment. Oh, I'm not inside function. That would be why. That'll also be helpful. Okay. So we'll just dump the contents of the file out to the screen just to make sure that we are actually reading the file, because that's super helpful to actually be able to read the file. Let's see. Let's set the right project. Do that again. Oh, that's nice and small. All right, so here's our text file. We're reading the file. Step one, we're good. We can find the file. That's always one of the tricky things you when you're writing applications, making sure you can actually find the code file. If you are using Visual Studio, and depending on the version of Visual Studio, usually context that you're running in is the same as the context as the executable. That's not always the case. C++ might be over here where the project file is. That's why it's always best to actually prompt the user with what they want to open up so they can give you the path of where things are. And load from the user. So if they go ahead and that file path, and I run this again. And give the path, full path, and then it works whatever machine you're running on. So you always have to be careful with files. If for some reason you're getting stuck on reading from the file, just go ahead and create the array of strings and then iterate over the array of strings. Otherwise, the interpreter, right? So align something like Rx equals 4. So what we want to do is look at the pieces of the word. Look at the very first token. And we'll assume that they're doing all uppercase like they should. It's always a good idea to make sure that one of our scenarios is they are declaring a variable. Let's see. The background compiler is annoying. We're talking about program 4 and the basic program structure to deal with reading from a file and breaking that file apart so that we can do stuff with it. On the variable, right? Right, and we're just breaking things apart. You got right down the variable. To mean its value is value. So now I run the program. Interesting. The default size is 36. Windows so tiny. Okay. All right, so we're at a program. And right now it only understands the var keyword. We found the variable x, and it has the value 4. So if we were to, right, we wouldn't be printing out in our interpreter. We would just go ahead and add name with value to the hash table. Then we should move along to other keywords. Same idea. On the word print, and print handles print, and then a variable, whatever that is. Doing similar things, we'll go ahead and get the name, which is the second token. Token is the 1. And then we just do a lookup. Lookup in the hash table. If found, read the value and print it out. Found the variable plus name. And we have to see the same. Oh, brand new 1. Right, run it again. Right, found the variable x from the declaration, found the variable x from just doing the read. Right, again, our code file is very simple. And this is the way you want to approach the application. Don't try to do the sample. Here we go, right? Don't try it with the first sample application, right? Com's also easy. If com just ignore things, there's nothing else to do, just go to the next line. Right? When you get to start, you need to add a scope, so you're going to want to do something somewhere you need to keep track of scope. Start at 0, 1, or something along those lines, so they can help figure things out. Right, case com, keywords you have to worry about. We have start keyword. And we have the finish keyword. Start finish com var, print, right? Total our keywords. And then if it's not a keyword, then it's variable equals expression. That means name is now token 0. You need to figure out expression is just variable, or is it a literal, or is it a binary expression? Okay, so this is more or less the interpreter. Of course, there's more girth to fill out here in the body. You need to go in and grab your linked list code from the beginning of the semester, wrap it into the hash table, chaining hash table, and this is a chaining exercise. Add your classes for that. You probably want class for variable, class for your list, possibly your list node. Redoing that. The list. Class for your hash table. And then the interpreter just has the hash table inside of it. For scope, there's a couple ways of doing it. Some people prefer to create a hash table for every scope and then rip through each hash table trying to find the variables. So that's Yeah, I recommend it. Use one hash table. And what you do, let's say we go ahead and create X with 5 or 4 or whatever. And we add it to the list. And this X is the value, X is the name, 5 is the value, and 0 is the scope. What happens if I say, let's say I have program Rx equals 5. Start Rx equals 10. X, finish, and print X. All right, so we get to our first bar X, you create the variable, you add it to the list. All right, that's in our list. We get to a start block, so we're now in higher scopes, or lower scope. Scope 1, scope 0. We need to go ahead and create another box. And I copy that. Oh, that's kind of, anyways. Select. And I'm going to move this over. So what I'm going to do, I'm going to create the next variable. Also is X. This X has a value of 10 with a scope of 1. All right, so when we print X, the value that we should be printing is 10 because 10 is closer in scope. This version of X is closer in scope than the one that's in the outer scope, right? Typical scope resolution rule. So when we do look up X hashes to this first list, we come into our table, you see I'm looking for X. Let's put that X over here. I find X, and then I print out the 10. By inserting new values that collide at the beginning of the list, it's A faster, and B, it is in alignment with our scope resolution rules for our lookups. So when we come along, we printed X, we spit out 10, we finish. When we finish, scope 1 goes away. So each list that has any scope 1 variables, they need to go away. And deleted from the list. We come down here after the finish, print X. Do our lookup, find that goes to the first list. We have a match, and we spit out 5 at that point. Alternatively, you have your list or your stack of hash tables, and you have to look up and do a match. I recommend making your hash table super small so you guarantee the collisions. That way your collision resolution handling is known to be correct. Otherwise, that's about all I need to give you tonight, both lecture and talking about program 4. This one is still more code than the ones before it, so you want to start hacking away at it. You have to work on a simple program. 2 keywords, var and print. And then once you have those 2 keywords, you start expanding the language, right? If you want to do scope next, or you want to do complex expressions next, whatever. If there aren't any questions, the balance of tonight is just lab time. Use for program 4. Otherwise, I'll see you next week. And double check your test. Make sure I fixed things. I just went ahead and get everyone 2 points for that typical question. And so that should show up on your test score at the end. Yep. All right, so you can still hear me. Have a good night. Take care.